Let's talk about drawing both chair conformations for substituted cyclohexane, whether it's mono, di, or tri or tetra substituted. Now, something to remember, once you have a substituted cyclohexane, the chair conformations are not equivalent because they have different energy. Now, that topic is covered under the video that says chair stability, right? Now, to draw the two chair conformations, you need to draw the lines that I spoke about in my video on drawing chairs. So let us draw one methyl cyclohexane and let's draw the two chair conformations. So to draw the two chair conformations, then you can go back and review this. Draw two parallel lines, not directly under each other, right? Then you connect the parts that point up with a V down. Connect the parts that point down with a V up. That's one chair conformation. Draw two parallel lines in the opposite direction. As you could see, the arrows that point up is pointing this way, the opposite from the other one. Connect with your V down, connect with your V. These two chair conformations, they're in equilibrium, right? So right now what I've drawn is cyclohexane. Now I need to put on my methyl group. So I am going to stay on the nose. It makes it easier to see things, all right? So axial bond points down, equatorial bond points up. You should remember where the bonds meet pointing is the direction in which your axial bond goes. To draw one methyl cyclohexane, you could have put the CH3 on any carbon. Any one of these carbons would have been fine, right? I just want to stay on the nose for explanation purposes. Now, let's find this carbon right here. Let's find this carbon over here in the alternate chair conformation, right? So your nose is here, but what happens to the nose over here? Notice it's now pointing up. It moved from here to up here, so it moved up this way. So the chair is rotating in this direction, right? So let's number these carbons, right? This is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. So your chair rotated, right? So carbon number 1 in the alternate chair is right here. Carbon 2 is here. Carbon 3 is here. So it's 4, 5, 6, right? So because it's your flip, right? Also, you could go over to your nose for 4. What happens to this bond? It drops down. See that? Nose is up here. In this one, it's down here. All right? Now, let's talk about what happens, right, once you have the chair rotating. Let's talk about what happens to these bonds, right? So, something to remember. When the chair rotates, your axial bond become equatorial and vice versa. If it's up, it will stay up when the chair rotates. If it's down, it will stay down when the chair rotates, right? So let's look at what we have. Your CH3 is in the axial down position. So this is axial and it's down. This hydrogen right here is in the equatorial position and it's equatorial up. All right. Now, let's go over to our rotated chair. Remember, if it's axial, it becomes equatorial. If it's equatorial, it becomes axial. And if it's up, it stays up. You can always put your bonds on because I know right here there's an axial bond that points straight up because the lines meet pointing straight up. Equatorial bond points down. So on carbon number 1, over here when my chair rotates, my CH3 needs to be in the down position. And remember, if it's axial, it becomes equatorial. The only bond that is down over here in this chair is the equatorial bond. So your CH3 is right here and your hydrogen is right here. So you need to remember, right? If it's axial, it becomes equatorial when the chair rotates. If it's up, it stays up. So your CH3 here is down, it stayed down. Your hydrogen here is up, equatorial up, axial up, okay? You need to remember that for your chair. All right, let us look at a chair, right? So by the way, these are the two chair conformations for one methyl cyclohexane. Remember, your conformation, same molecular formula, connectivity is the same, but clearly there's a difference in the orientation or the arrangement. Once that chair flips, here's original chair, when it flips, this is a different orientation, right? These are different in orientation, and the carbons of the ring too are now oriented differently. Let's talk about, let's look at an example with three. Let's do something with three substituents, all right? I'm gonna just erase these. We can keep the numbering, and I'm gonna keep your info right here, all right? So let's go. Let's look at, let's put a hydrogen here, a CH3 here. Let's put on carbon 2 ET, sorry, ET, see why this is happening. ET, T stands for ethyl. And let me erase this because this is not the name of what we're doing. And also the direction in which I'm numbering on my chair right here is not the direction I would number if I'm naming. I'm sure you know that because you've watched my videos on how to name and you're a pro. CL. All right, CL. H. So if you notice, I knew where the axial bond would point, where the equatorial bond would point. If you've forgotten, go back to the video on drawing chairs. Let us now take a look, right, at what happens to these bonds when we rotate the chair. So we already numbered. This is one. So this is one, two, three, right? It flipped this way. So the chair rotated this way. This is 1, 2, 3, 4. 1, 2, 3, 4. So let's take care of everything here. On carbon number one, we have a CH3 that is up. It needs to stay up. So your CH3 on one has to be in the axial position. That's the only bond over here that's in the opposition. The equatorial is what's down. So this is your hydrogen, right? Carbon two, we have an ethyl group, and the ethyl group is in the axial opposition. So over here, it needs to be in the opposition. Let's see which bond is in the opposition. Your axial bond points straight down here, and the equatorial bond is the one that points up. So your ethyl, which is up, is going to be in the equatorial position. It's the only bond that's up. Remember, up stays up. Axial became equatorial. And then we have our hydrogen. Let's find carbon number 4. Carbon 4, where the nose dipped. Here's 4. On 4, I can always put my bonds. The axial bond point down, equatorial point up. Over here, my hydrogen is what's up and it's in the axial position. So in this chair, over here on carbon 4, the hydrogen is what's going to be on the equatorial because that's the bond that's up. And your Cl is down equatorial, so it must be in the down axial position. So this is how you would do your chair conformation if you have mono or disubstituted, or if it's trisubstituted. Let's talk about, let's just say they give you, I want you to be able, right? If they give you two chairs, I want you to be able to know the direction in which the chairs are rotating, right? Because sometimes they will not ask you to draw the chair, they'll give you the chair. So I need you to be able to identify if chairs have rotated. This is cyclohexane. All you have to do is find the nose. Just find the nose. both of them. And look what happens to this nose, right? This portion of the molecule is on my right. Is on my right. Go to the right of the molecule and look what happened to the nose. This nose, it dropped down here. I'm gonna call this one. All right. Go to the other nose on the molecule, right? It's down over here on my left. Go to the left of this molecule, right? And this is how I'm sitting looking at it. The nose down here moved up here, right? I'm going to call this is carbon 4. This is 4. This is also 4. So if you are ever given something and you're like, oh my gosh, do I have different conformations? Look and check to see if the chairs rotate, right? Stability will cover, chair stability will help a lot with determining if you actually have conformations or if molecules are the same. Where I am going to do a video on that.